Welcome to this session. In this lecture, we will learn that how to calculate entropy change in different physical processes, in different thermodynamic processes. Fine. So, before starting this, we have to, our concept should be very clear. So, here we have one standard equation ds equals to del q upon t plus s generation So what do we understand by this s generation? This is because of internal irreversibilities present in the system. This is because of external irreversibilities present in the system. Okay, so if the system is adiabatic, then what is going to happen? Del q will be 0. Okay, and if system is reversible, then s generation term will equal to 0. Okay, and if I take a system which is adiabatic plus reversible, then we get ds equals to 0, right? So when entropy change is 0 or entropy remain constant, we call this process as isentropic process. Okay, so the funda is, if I will add 0 plus 0, we will get 0, right? But so if process is adiabatic plus reversible, then we must get one isentropic process. Now in another case, if a process is isentropic, then we cannot say that this process it must be adiabatic and it must be s generation, it must be reversible, right? So we know this s generation is always positive. So what we can write, if we can get 0 only and only if this s generation is always positive. This is like this combination. So here there is some external irreversibilities present in the system, and some internal irreversibilities are also present, but overall effect will be what? The net effect will be 0. This means this process will be isentropic in nature. Okay, so this is one important point. So let's explore some more important point. Okay, now let's see, if we have a universe means there is no heat interaction. This is adiabatic in nature. Then how we will write a change in entropy for this? This will be del q upon t plus s generation. Okay, and in this universe we have one system and we have one surrounding. Okay, so what is going to happen? So change in entropy for universe, this will be 0 and we will have only s generation. Then what we can write? ds of universe will be s generation, and this will be equals to what? ds change in entropy of system plus change in entropy of surrounding. Okay, so this is a very important concept in entropy calculation. Okay, so in entropy change calculation, We have four types of questions. This is type 1, another is type 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 2, type 3, type 4. Okay, so in type 1 what we have discussed, that it will be for a universe, and here we have one system, and here we have surrounding, right? So what will be the governing equation for this? So we have, as we have written earlier, ds of universe will be equals to s generation equals to ds of system plus ds of surrounding. Okay, so this is one relation. So this is for type 1. Now let's explore what is the physical phenomena present in type 2, type 3 and type 4. So in type 2, the physical phenomena is like this. Here we have one water bath. Okay, and here we have one metal cube. Here we have one metal cube. This is submerged. This is submerged in water. Okay, okay, now let's take the metal cube having mass m1, heat capacity as C1, and it is present at temperature T1. And this water is having mass m2, heat capacity is C2, and it is present at temperature T2. And we are assuming that the initial temperature of this metal cube is higher than the water. Okay, अच्छा, यहाँ पे क्या होगा? यहाँ पे the energy will be lose. This metal cube will lose its energy and water will gain some heat energy. So the first point is conservation of energy. This will be what? Heat lost by metal cube will be equals to heat gained by water. So it will be heat lost by metal cube. So okay, so it now what is the funda? When it will achieve a thermal equilibrium, the final temperature will be Tf. Okay, so now let's write the equation. Now the heat lost by metal cube, this will be m1 c1 T1 minus T final equals to m2 c2 this will be heat gained by water. This is equation 1. Okay, and if I write change in entropy of metal, so this will be So this will be, so we have this TDS relation, TDS equals to du plus pdv, and another TDS relation we have TDS equals to dh minus vdp. In case of this, in case of solid and liquid, these are incompressible in nature, so change in volume is 0, and we write du as mc dt. Okay, so from here we can write ds equals to mc dt upon t. Okay, so this is the standard equation. And in case of for what, in case of ice, now let's write it for ice. Just integrate it from t1 to tf. Okay, we will get mc ln tf upon t1. This is equation number 2. This is what change in entropy of let it be metal, change in entropy of metal. Okay, now what will be the change in entropy of water? This will be mc dt upon t. Okay, in case of water, water is initially at temperature T2. It will increase up to T final. So this will be what, mc ln tf upon T initial, or sorry, tf upon T2. So this is relation equation 3. So we will use these three relations for calculating the change in entropy of metal and change in entropy of water. Okay, so this is type 2 problems. Now let's come to type 3 problems. In type 3 problems, type 3, in this type 3 problem we will calculate entropy change for an ideal gas. So we know that we have relation TDS equals to du plus pdv. Okay, we have relation TDS equals to du plus pdv. Now just write it, ds equals to, this du will be what, mcv dt. This will be divided by t plus p dv divided by t, and we can write this mcv dt divided by t plus, now from ideal gas, if this is following ideal gas, can we write pv equals to mrt, right? So p by t will be what, mr by v. So this will be dv. Okay, now what we have to do, we have to just integrate this. This will be from t1 to t2. This will be from v1 to v2. Okay, for those students who are having problem in integration, the funda of integration is like this. If we have a function dx upon x, it is integrating from x1 to x2, we will get ln x. फिर ये कहाँ से कहाँ तक जाएगा, x1 to x2, we will get what, ln x2 minus ln x1. This will be ln x2 by x1, right? So this is ln, this is ln, this is at base e log base e x2y x1. okay, so this is the concept. So this v will go from v1 to v2, and this r is what characteristic as constant. We will explore in the numericals. okay, so finally we will get s1 to s2. We will get s2 minus s1 is equals to cv ln t2 by t1 t2. This will be what? m cv ln t2 by t1 plus mr ln v2 by v1. okay, so this is for entropy change. If we divide it by m, so this will be what? This is change in specific entropy. This will be cv ln t2 by t1 plus r ln v2 by v1. So we have discussed earlier that this TDS relation is valid for both open and closed system. It is valid for both. okay, so let me erase this. So now this was first TDS equation. Now another TDS equation is TDS equals to dH minus VdP. TDS equals to dH minus VdP, and in case of ideal gas we can write dH as mCp dt minus, and for now what we do, just divide it by, if I divide it by t, so this will be what? V by t. okay, so this will be what? V by t. So from this relation we get V by t equals to mr by p into what? dp. And then okay, so what we have to do, similar, integrate it from t1 to t2 and integrate it from p1 to p2. okay, so we will get the following relation. Integrate this entropy from s1 to s2, so we will get relation s2 minus s1 will be m cp ln t2 by t1 minus m r into ln p2 by p1. so this is the relation 2, this is relation 1. okay, so these are the two important relation for calculating the change in entropy for ideal gases. okay, so now let's come to another concept. okay, type 1 हो गया, this is type 2. अच्छा यहाँ पे the important point here is to remember here, जैसे जैसे यहाँ मेटल का टेम्परेचर डिक्रीज हो रहा है, एज द टेम्परेचर ऑफ मेटल इज़ डिक्रीजिंग, द हीट लॉस्ट बाई दिस मेटल इज़ ऑल्सो डिक्रीजिंग. सो यू कैन सी फ्रॉम दिस रिलेशन, जैसे अपन टी को डिक्रीज़ करेंगे mc/dt भी डिक्रीज़ होगा. ठीक है, इसीलिए ये अपन इसको इंटीग्रेशन कर रहे हैं. जहाँ पे हीट सिंक का कंसेप्ट आएगा, थर्मल रिजर्वायर का कंसेप्ट आएगा, वहाँ पे टेम्परेचर कांस्टेंट रहता है. आई विल डिस्कस दिस पॉइंट. सो कि ये दिमाग में रहना चाहिए कि ऐसा नहीं होगा कि इसका टेम्परेचर कांस्टेंट रहेगा. आई विल डिस्कस दिस पॉइंट इन द क्वेश्चंस, राइट. सो दिस इज टाइप 3. नाउ लेट मी अगेन राइट इट very clearly. So in type 3 we we are taking only change in entropy. Okay, so this will be m cv ln T2 by T1 plus R ln V2 by V1. Okay, this is relation 1, and another relation which generated from TDS equals to DH minus VDP was, this will be MCP ln T2 by T1 minus MR ln what, P2 by P1. Here M will be there, right? So this is relation 2. ओके, और क्या इसमें है? ओके, अच्छा, इसको याद करने की ट्रिक कैसे है? टी डी एस इक्वल्स टू डी यू प्लस पी डी वी एंड टी डी एस इक्वल्स टू डी एच माइनस वी डी पी. ठीक है, सो ये क्या होता है यार? डी यू को कैसे लिखते हैं हम लोग? एम सी वी डी टी. और डी एच को कैसे लिखते हैं हम लोग? एम सी पी डी टी. ठीक, तो P है यहाँ पे, P के साथ P आएगा. V है यहाँ पे, V के साथ V आएगा, राइट? एक कंसेप्ट ये, और ध्यान रखना, CP इज़ ग्रेटर देन CV, CP इज़ ग्रेटर देन CV. तो DH वाले में से निगेटिव वी विल सब्सट्रैक्ट दिस VDP. ठीक है, बिकॉज CP इज़ ग्रेटर देन CV, सो वी हैव टू सब्सट्रैक्ट सम क्वांटिटी एंड वी नो CV इज़ लेस, तो CV की जगह अपन ये प्लस ऐड करेंगे. सो ऐसे अपन को ये दिमाग में ध्यान में रखना है. सो दिस इज़ व्हाट टाइप 3. नाउ लेट्स मूव टू टाइप 4. Type 4, this is entropy changes. In open system. In open system, अच्छा यहाँ पे क्या होगा? As we have learned earlier, in open system, so how was the diagram for open system? So here we have one container, fluid is coming from here and it is leaving here. So this is our control volume. This is our control volume and this is exit point, we are calling this, and here's mass flow rate is E. If there is a dot on the physical quantity, it will be what? Mass flow rate, m dot E. This is exit, this is inlet, and we are taking mass flow rate here as m dot I. Okay, so from from mass balance relation, so from mass conservation, we can write dm by dt equals to what? M dot I minus m dot E. Okay, this is mass conservation equation, and another is energy conservation equation, which we have, I think, learned in open system. So this is dE by dt, this will be equals to q dot, and suppose this is q is interacting and the work done by the system is w. This is rate, so this is this minus this plus m dot inlet, plus z1, the height from this base to this point is z1, plus c1 square by 2. I am taking this c1 square by 2, okay, plus hi, this is inlet enthalpy, minus m dot out, this will be z2, plus c2 square by 2 plus h exit. Okay, this is relation 2. This is energy balance equation for open system, and if it is steady state, this will be 0, this will be 0. And the last equation is entropy balance for this open system. So we will write ds by dt or ds dash ds dot, it will be equals to del q by t plus s generation dot plus m inlet dot into si minus m of exit dot into s exit. Okay, now what is happening in case of steady state? What is going to happen? This ds by dt will be 0, this will become 0, right? So what we can write, though, so this relation will converted into this m dot I si minus m dot e se equals to, okay, so this will be minus times del q upon t dot plus s generation dot. Fine. So if this is what initial inlet entropy, this is exit entropy, right? Now if we take negative sign here, it will be this will interchange, and we can write this is what specific entropy here. This is specific entropy, this is specific enthalpy, small h is specific enthalpy. So this will be what se minus si equals to del q upon t plus s generation, right? So this is the relation for open system. This is for steady flow. In case of steady flow, open and closed system, the equations are same. Okay, so this is for, so we will solve these, we will solve the numerical based on this: type 1, type 2, type 3, type 4. So this is all for today.